ready for the exam?
No.
But you have to take the exam. Okay, so let's, I will try to, first half maybe we'll go over little bit more material, and then second half we'll go little bit deeper. So that will be easier. If you have followed the class, everything what we discussed in the class in detail, then you should be able to do very good in the exam. So read following the class as guidelines. So we are in the lipid synthesis. I guess we are talking about the icosanoid biosynthesis using cyclooxygenases. So icosanoids are the family of lipid-based signaling molecules, lipid-based hormones, variety of function, and this is synthesized from arachidonic acid with the help of cyclooxygenase. So you form a 5-member ring, cyclization, and the oxygen addition. That's why it is called cyclic addition of cyclooxygenase. You want to know this chemical reaction. Okay, draw, practice 2-3 times. It should be. You should be able to draw it. Now, this prostaglandin biosynthesis is critical because this acts as signaling molecule for variety of purposes like inflammation. If there is a cut or joint pain, correct? There is swelling or inflammation. You see some of the prostaglandins are produced. Okay, so if you can inhibit the prostaglandin production, the inflammation will go down. Does it make sense? So basically the way it is done, if you inhibit this, I think this is correct. If you inhibit this cyclooxygenase, so you actually stop the production of prostaglandin, your inflammation is low, and you feel less pain. And that we discussed the basic mechanism by which you can control the inflammation and pain. And there is a whole class of drugs, correct? Almost all of us will have some inflammation, pain, correct? We try to take some medicine, and most of the time we take something called non-steroid anti-inflammatory agents, and they basically inhibitor of cyclooxygenase. Most common is aspirin, Tylenol, ibuprofen, all of them, whatever you talk, the over-the-counter medicine you take, they actually are inhibitor of cyclooxygenase family of enzymes. They inhibit the production of prostaglandins, and the way it does is here, the cyclooxygenase active site, the serine group, the serine group reacts with acetyl salicylate, which is aspirin. We did the chemical reaction other day, correct? So this hydroxy group reacts with this, attacks this carbon with carbon, the acetyl group, so that it gets acetylated. Does it make sense? Once the functional group is acetylated, it cannot catalyze the production of prostaglandin. So that inhibits, okay, the inflammation and pain. So that's a standard, very well studied mechanism of aspirin. Okay, aspirin has a lot of other application as well. Okay, can you name some other application of aspirin? Other things.
Blood thinners.
Blood thinner. A lot of people use aspirin as blood thinner. Okay. So people who are especially higher risk of cardiovascular attack, high cholesterol and so on, they take some aspirin. But it has lot of side effects. Correct? Most of the time, when you use a foreign molecule in our body as a drug, it attacks two organs very badly. First one is liver. Because everything what we take, okay, your body has to deal with it. It's not that, correct, you take and it goes out. Whenever a foreign molecule or drug we take, your liver, our liver, has to metabolize it so that either it can be utilized by the body, if it can, as a source of nutrients, or if it cannot, it has to excrete it out so that nothing stays in the body. If it stays, it's a problem, correct? So the way it does, let's say you are exposed to certain molecules which is like this, or aromatic molecules. These are highly hydrophobic. They cannot go out. Does it make sense? But still liver try to do all kinds of stuff so that it can let it go out. What does it do? Anybody has any idea? What are the enzymes liver has? No? But if you take a lot of these extra soft drinks and all kinds of fancy chemicals, food we take, correct? They have a problem. That's a problem for the liver, even if it is tasty. So liver has a lot of oxidoreductase family of enzymes. They sometimes add some functional group in these molecules. If molecule is hydrophobic, to make it water soluble, to excrete it out, you have to make it water soluble so that, correct? So they add some oxidation, all kinds of stuff, add some additional group so that it becomes hydrophilic and excrete it out. So that's why whenever we are taking a foreign drug, the cytochrome family of enzymes, cytochrome P450, cytochrome A, B, C, correct? Those are oxidoreductase. Those oxidoreductase enzyme level goes high in the liver. When people drink alcohol, right? Alcohol needs to be also metabolized it out, right? The liver gets insulted because liver has to work hard, right? If somebody is constantly taking alcoholic, their liver damage takes place, their oxidoreductase level goes high, and if we keep on constantly insulting the liver, at some point liver will fail. Correct? So I tell a story and take some time. Maybe good story. Yes.
Does ibuprofen inhibit the cycle of oxygen?
Yes, I'll come to that. Okay. So I have a story in mind. So let me finish, otherwise it will forget. So I was researching in an organic lab. Organic lab use a lot of ethanol, lot of methanol and all this stuff, correct? So ethanol is good, everybody likes it. So we had a lab attendant. His name is Francis, little bit in the range of 60s or so, okay? So his job was to carry the ethanol, methanol, all these solvents from the store to the lab. And Francis realized, wow, this drum is ethanol, correct? So he thought, let's take some out because ethanol is good. And he every time brings an ethanol drum, he takes some out, and quite time he enjoys, you know. And this has been happening for a couple of years, and all of a sudden that his eyes are red, liver is getting damaged, and so on and so on. So he was freely consuming some ethanol and having a good time. The problem is that the ethanol, which is commercial ethanol, is not 100% pure. To avoid people drinking, they mix tiny amount of methanol. So methanol is terribly dangerous, correct? So he was getting liver damage, neuronal damage, all kinds of stuff. But even without this methanol, right, one has to be careful because ethanol can do all kinds of stuff as well. So why I am going out of the path? So these molecules inside the liver. Aspirin has lot of side effects. It can damage the liver, it can damage the kidney, and all kinds of stuff. So, but still, we have headache, we have pain, so we still take it, even if, correct? It does insult our liver. But if you take once in a while, few tablets is fine. That's why it is suggested that you don't take the painkiller for long time. There is another side effect of taking Tylenol that it could do if somebody is regularly using these NSAIDs, they have stomach bleeding, all kinds of stuff. So it's good to take care. Take once in a while if you need, but it's not good to take a lot of these painkillers on a regular basis. So if you look at this structure, there is an active acetyl group which could be transferred. If you look at the acetaminophen is the Tylenol active ingredient, right? So it also has the acetyl group which gets transferred to the cytosol. So acetaminophen also blocks the cyclooxygenase active serine. So that's how it inhibits the production of prostaglandin and reduction in inflammation. Does it make sense? Ibuprofen, you want to know the structure of acetaminophen, aspirin, ibuprofen. Know the structure, know the mechanism. How does it help? Correct? I can ask. Draw the structure of ibuprofen or Tylenol or aspirin and tell me how it helps reducing the inflammation and pain. Can I ask? Yes or no? See, you already got 10 points. These are 3 response questions. So now if you look at the ibuprofen structure, it actually does not have this active acetyl group. Correct? So how does it reduce? What is the mechanism of inhibition? Slightly bind to the other side, allosteric side. Correct? Enzymes has an active side where your substrate binds here, but also enzyme could be inhibited by binding to some other side. Does it make sense? These are called allosteric inhibitions, and when you screen the molecule, you can identify what structures it may inhibit. Some of them are correct, competitive, some of them are non-competitive, mixed competitive, allosteric. Does it make sense? So there is a ton of other drugs which are used. These are at this age when you are young, 20, 30, 40, Tylenol aspirin works pretty well. But if you are 60, 70, the age of Tylenol is slowly going. Okay? Then what is the painkiller used? Anybody? Aleve? What is the active ingredient there?
Naproxen.
Huh?
Sodium naproxen.
Sodium?
Naproxen.
I think the most maybe that is used may be stronger. I don't know the mechanism of action, but towards the stage when we are living longer and we have a lot of chronic pain on a regular basis, people use these morphine type of drugs, which are, correct? When people are living 60, 70, 80, 90, they have a lot of pain. At that time, none of these medicine works, and they use these. Initially started low dose of morphine. You know, hydrocodone? People who break the bone, correct? When they are going to bone surgery, doctor gives them hydrocodone because those are the strongest painkiller you can think of. correct? So those are nothing other than some of these drugs because they keep you in the sedation, correct? So eventually you slowly give some drug, it reduces the pain, but as you get older, you need to increase the dose of this drug. But these drugs, eventually, people get addicted. They get addicted because of the morphine, heroin, all these nasty drugs, correct? So there is not really any good drug, pain medication, which is effective, but not lead to addiction. The addiction is a big problem. Even Tylenol, people get addicted. Tylenol damages liver. Tylenol, few years ago, it used to be available for infants, the low dose Tylenol, but now you cannot buy for infants low dose Tylenol because it has so much severe side effects. So if you can develop certain medication, pain medication, it does not lead to addiction. You can be millionaire or billionaire without much problem. Because a lot of people with youth, we all are living up to 100, 110, 20, 30, 150. Correct? So we'll need a lot of some of these. I don't want to live that long. So, but we like to do that. So many of these pain medications are good, bad, but NSAIDs are very important. I discussed, correct? Non-steroidal anti-inflammatory drug. Now, I'm sure all of us had fever and we took Tylenol and ibuprofen, correct? Anybody can explain how Tylenol reduces the fever? No? Okay, this is your homework. Good. I will not ask this question. There's little bit signaling mechanism, cytokines, regulation. We have in brain which controls your body temperature, and there is a lot of things signaling goes on. Okay? Read this and tell me in the next class. So I may ask you the mechanism of Tylenol, acetaminophen and aspirin. Now let's go back one more slide. So these are all different types of NSAIDs. I want you to know the structure of aspirin, ibuprofen, and the Tylenol, which are common. Now I want you to pay attention to another very important point, that prostaglandins are required for inflammation. So if you inhibit, you reduce the inflammation and pain. So you are inhibiting here arachidonic acid to prostaglandin by cyclophosphamide. But arachidonic acid, it's a lipid, unsaturated lipid. It is actually initially present in the form of lipids, esterified lipids. Okay, so it's in the form of so you have arachidonic acid. This is the form okay, this is in the form of ester. Okay, part of the lipid, and this needs to be, this arachidonic acid lipid needs to be freed, correct? So it needs to be hydrolyzed, and the enzyme which does is PLA2. PLA2 activates an water molecule which hydrolyzes the releasing free arachidonic acid. Unless you have free arachidonic acid, even if you have cyclooxygenase, it's not going to produce the prostaglandin. Does it make sense? So if, instead of arachidonic acid, if you also inhibit the phospholipase A2, which will inhibit the production of arachidonic acid lipid, you should be able to inhibit the inflammation. Does it make sense? So this is another target. So cyclooxygenase is a very important target for non-steroidal anti-inflammatory drug. Same could be the inhibition of phospholipase A2 may have potential in reducing the inflammation. Does it make sense? Yes or no?
Yes.
Okay. So at least you have learned two targets where you can, correct, make millions of dollars. Correct? And give me 10%. All right. So there are many other drug targets which we are not talking here for inflammation and reduction of pain. Next, we are all talking hot topic. We have discussed the pain. Now we are talking about the cholesterol because it's a very hot topic. Cholesterol is a natural lipid synthesized only in animals, and about 20 to 30%, about 28%, not 20, about 28% of the cell membrane, mammalian cell membrane, has cholesterol. But if the cholesterol level is high, if it is circulating in the body fluid, it eventually develops in plaques and blocks the circulation. That's the stroke. So if it blocks the circulation, there is no oxygen supply, organ failure and death. So always people try to worry about lowering the cholesterol. So cholesterol is biosynthesized from acetyl-CoA. We'll study the biosynthesis of cholesterol, and then we will briefly touch this, how you can target this biosynthetic pathway to develop drugs for lowering cholesterol, because that's also a $1 billion drug market. So I think we have done part of it. It shares the half of the pathway with ketone body synthesis. Okay, so you have CH3COS COA, acetyl-CoA, and this proton is acidic. Base can take this proton, you produce this reacts with an acetyl-CoA, COS COA, you produce this, correct? So you have CH3CO, CH2, CO, COA. Does it make sense? Now it can react with another acetyl-CoA deprotonated. We have done this reaction in ketone body synthesis. So you produce S COA, COCH2, CH, OH, CH3, CH2, CO, S, it could be hydrolyzed. Eventually will produce This you have studied. This is your HMG OA. This you have studied in ketone body biosynthesis. Does it make sense? HMG OA. So up to this, it is same as your ketone body synthesis. But HMG OA is a major intermediate in cholesterol biosynthesis. This HMG OA is reduced. This thioester group is reduced to corresponding CH2OH. Next step. So this thioester group is reduced, reduction to corresponding, or let's do CH2, CH, OH, CH3, CH2, CH, OH. This particular ester, thioester group is reduced. Reduced means it needs some NADH or NADPH plus a reductase family of enzyme, correct? HMG OA reductase. HMG CoA reductase with the help of NADH or NADPH, it reduces this thiol group. Hydroxy methyl glutaryl CoA, and this particular molecule is called mevalonic acid. Or mevalonate. Mevalonate is a kind of precursor of so you have mevalonate. Let's draw the structure again. CH2, O, this is OH, CH3, CH2, C, H2, OH. This is the mevalonate structure, correct? I copied from that side. Now this is minus. This can so you basically lose a carbon dioxide from here and followed by loss of a water molecule. You can actually produce CH2 double bond CH2 OH. Is it clear? Yes? Are you following me? Yes or no? Okay. So what type of molecule is this? It's very close to, it's a precursor. You can lose another water molecule from here. So you are producing actually this molecule. Does it make sense? So you are actually producing a derivative which is close to isoprene, which could be easily act as precursor of correct cholesterol lipid biosynthesis. Okay, so mevalonic acid, what I am trying to say, mevalonic acid is not really isoprene yet, but it is a precursor for a lot of these terpenes, terpenoids, and steroid-like molecules. You have some question?
I'm just trying to figure out your drawing. Is the B attaching the H and that's the bond that you erased, or is that just like an accidental?
Which one?
For the not the very bottom section.
Here?
Down.
Yeah?
Yes.
Oh, base is attacking this proton.
Okay, and then the proton gives its bond, right?
It bonds, it goes here, and that
Okay.
takes the electron that bond goes. Okay? Does it make sense? So mevalonic acid is a precursor for lot of these terpenes, terpenoids, including cholesterol. Next, if you look at it, I don't want you to, I don't expect you to know detail. So you start with this mevalonic acid, which is this structure. Go all now a couple of processing. I like this pathway, but I think it could be too much for you to remember for the exam. Okay, so this mevalonic acid gets phosphorylated, diphosphorylated, lose the water carbon dioxide. Okay, it becomes isoprenyl. Somewhere it becomes isoprenyl pyrophosphate. Eventually forms the farnesyl pyrophosphate, and eventually many farnesyl group, two farnesyl groups combine to form a molecule called squalene. Okay, what it is doing is that this monomeric form is preparing to combine dimeric, trimeric lipid. Does it make sense? So these monomers are combining to form dimer and trimer. Then two of these trimer combines to form longer lipid, which is called squalene. You can see the periodic methyl group CH3, 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 CH3. Does it make sense? It is coming from isoprene-like precursor. So squalene is processed to form mevalonic acid is processed to form the squalene. It's good to know this if you like. Okay, the squalene actually, once you have produced, you can just rewrite that structure in this form. This is squalene, the linear form. You can just rewrite. You can see this is actually ready to form the 6-member rings. Okay, eventually these bonds are connected here, here, and here. So you form all these 6-member, 5-member, 6-member, 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 and 5-member. There is little more to that. This double bond gets epoxidized with epoxidase family of enzyme. Epoxides are, what are special about epoxides? What do they do? They break. That means they are highly reactive. That's exactly what it is happening here. Because you need to connect these bonds, right, to make the cyclization to happen. And that's why it is forming the epoxide so that electron flow can take place by a ring opening of the epoxide. So eventually it forms, this drives this cyclization through this epoxide formation, forms the first steroid structure which is called lanosterol. Does it make sense? So once you make lanosterol, it is processed to different other type of steroids, including cholesterol. So what, for your exam purpose, what I want you to know is, so the detailed chemical pathway, so starting from acetyl-CoA to mevalonic acid, okay, then there are many steps. You have to squalene, that's a long lipid unsaturated, many steps to form lanosterol, and many steps cholesterol. Is it okay? So I may ask you, draw the detailed biosynthetic pathway for cholesterol in our body. So I do expect, although I omitted a lot of the steps here, lot of the steps down, but I do expect that from here to mevalonic acid, we have drawn the detail. Name of the enzyme, name of the cofactors, name of the intermediate. Does it make sense? So we are producing HMG-CoA and then mevalonic acid. Detail. Yes.
So for the steps between squalene all the way to cholesterol, can you just write it like that?
Yeah. That's it. Okay. So that it reduces some workload, but you know, correct, the detailed pathway. But these are actually also very interesting pathways. There are a lot of things I cannot go in, but important. Now, so this is a multi-step synthesis of cholesterol. Now, cholesterol is a major problem leading to heart attack, correct? High cholesterol level. But recently there are a couple of controversial papers. They said cholesterol is not the cause of heart attack. I don't believe them, but everybody has freedom to say whatever they like to say. Correct? But cholesterol is a problem. High cholesterol is a problem if we are eating a lot of fatty food. Cholesterol is food which are tastier, but it's not healthier. So let's turn off the lights so that I can go back a little bit. So you have acetyl-CoA to mevalonate. You have done this HMG-CoA synthase thiolase to produce HMG-CoA, and it is reduced by the enzyme called HMG-CoA reductase. Now, we are so much concerned about high cholesterol. We have to reduce some cholesterol level, make some drug which can lower the cholesterol so that heart attack risk is reduced. One of the way one can do is inhibit the total cholesterol biosynthetic pathway. Does it make sense? If you produce less cholesterol, it has some chance of lowering cholesterol. But now it's a multi-step process. There are 10 different steps of lowering cholesterol lowering, biosynthetic reaction. If you want to inhibit, you have to inhibit an enzyme which will effectively, correct, reduce the synthesis. So which enzyme would you like to inhibit if you have to reduce the production of cholesterol? HMG-CoA synthase, one of them. HMG-CoA reductase is another of them. What about this? Thiolase. There are many other steps. All of you are right. I don't want to say all of you are wrong. But you are, but you are not very right. Correct? So if you have 10 different steps, you have to be smart to pick up one chemical reaction which will inhibit most efficiently. And you should tell me how would you select which reaction to inhibit? Based on what? How it affects other reactions. Anybody else?
The regulatory stuff.
Regulatory step. Which one is the regulatory step? How do you know?
Yes, sir.
No, you have to be a little bit smarter to answer. What? You are smart. Don't get me wrong.
Wow.
You have to give a smarter answer. So, what reaction would you, if you have 10 different, correct, there is a political leader. There are small leaders. If you want to control the whole politics, you better kill the big politician, correct? Or do something with that guy who is the bottleneck. You have to find the bottleneck, and you said it is the regulatory, but which one is the most efficient regulatory reaction based on kinetics or rate limiting step, correct? Rate limiting steps is the slowest step in the chemical reaction. So you have 10 different reactions, you have to find the rate determining step, and if you inhibit the rate determining step, then you can effectively inhibit the cholesterol synthesis. Does it make sense? So all of these, the HMG-CoA reductase is the rate determining step. Okay, that's why many big companies, Pfizer, correct, all kinds of big companies, they are actually decided, correct, that they inhibit this particular enzyme and to see whether they can reduce the cholesterol level and reduce or decrease the risk of heart attack. So, how you can inhibit? So you need to understand the mechanism, correct? You need to understand the detailed mechanism of cholesterol, HMG-CoA reductase, so that you can reduce, you can inhibit. Can you do the mechanism for this reaction? Reduction of this ester to corresponding alcohol, HMG-CoA reductase mechanism? Yes or no? So I don't need to do, correct?
No.
Let me do it. So HMG-CoA reductase is standard NADPH reaction. So this is your NADH or NADPH, correct? Now this takes the hydride, this hydride attacks here, correct? I omit two steps, but it will go like this. Electron flow goes like this, come back. That's how the chemist like to do. There is a tetrahedral intermediate. So you produce, I am not writing this side, CH2, CO, S, no, this is one. This one, correct? Yes? Then, what is that? Again another hydride transfer from NADH. And this will produce This will produce from here CH2, COH. Is it clear? This is a mechanism to NADPH hydride transfer to produce mevalonate. Reduction of these acetyl CoA to corresponding alcohol. Is it clear? Yes or no? So this is a mechanism. Now we have to inhibit this HMG CoA reductase for efficient lowering of cholesterol synthesis. So what are the different ways you can inhibit? One is, so you have to develop some inhibitor, correct? What is the efficient way to develop inhibitor?
Substrate inhibition.
Substrate binding you can inhibit, competitive inhibition. Am I correct? Now, if you look at the structure of the mevalonate, so this is the structure of mevalonate. It has an acid and an alcohol. They can do an intramolecular cyclization to produce some cyclic ester. What are the special names for cyclic ester? Alcohol reacts with a carboxylic acid to produce a cyclic ester. What they are called?
It's called a furan?
Huh?
Furans?
No. Esters react with an alcohol. I mean, the alcohol react with an acid, you produce ester. But if esters are cyclic, they are called lactones. Let's be little bit more chemical like environment. We produce cyclic esters or lactones. Let's see if I have. See, this is a cyclic lactone form. Now, there are many commercial drugs which are widely used for the treatment of high cholesterol, hypercholesteremia, and some of them are listed here. Is one of them is they're called, in general they're called lovastatin. This is the structure of, this is the mevalonate moiety, mevalonic acid, mevalonate. These are some of the known. Lovastatin, okay, simvastatin, lipitor. If you, these are different drugs which makes billions of dollars every year. Alright? Little bit high cholesterol, doctor likes to prescribe it. It reduces the cholesterol level, damages the liver, correct? Develops diabetes, all kinds. But company has made a lot of money because it reduces the cholesterol. Correct? Then they don't care what happens. So, but one good thing what you should look at it here is that in those structures there is something similar which are actually the lactone, mevalonic acid moiety. Either they are cyclic or acyclic mevalonic acid moiety. Does it make sense? Why? Because this is a, it binds to the binding site of HMG CoA reductase. Does it make sense? So that's how these molecules are selected as a drug. What is the function of other drug? Nobody, sometimes we know, sometimes we don't know. They have something to do with solubility, reducing the side effect, and all kinds of stuff. Whenever the organic chemists like to make something, they think this is the active site, it has mevalonic acid, and they made thousands of library of compounds, maybe making mevalonate acid derivatives and give it to the mice and see which one reduces the cholesterol most with least side effect. Does it make sense? And if it passes the mice, then it goes to the human population and then released into the market. After 30 years, we realized use of some of this drug causes the diabetes. So we did not die in cholesterol heart attack, but we are dying in diabetes. Correct? So this is an option we like to take and companies make the money. Correct? So active site of these cholesterol lowering drugs has a mevalonic acid moiety. And I want you to know the name of these, some of these like Lipitor, lovastatin, at least two. Very critically know that their active site has the mevalonic acid derivative. Correct? Yes.
Is it, so, mevalonate or whatever, it's a product, so is this like product inhibition?
You are right. I was expecting that question. Normally you start, substrate will bind.
Yeah.
Correct? Substrate analogs or product analogs both could inhibit because the product is not releasing, will not produce. Substrate analogs are also very efficient. What is the most efficient inhibitor based on enzyme kinetics?
Allosteric.
No. No. It is the transition state analog. If you studied your BIOCHEM 1, transition state analog is the most efficient inhibitor in lowering the energy, and somewhere this molecular structure has to have in between substrate and product life. Does it make sense? So these are based on the screen, so it's somewhere effectively inhibits. I think we need to review. We are going out of time. There's little bit of lipid transport I could not touch today. If we touch, then we cannot review. So let's review whatever up to this cholesterol biosynthesis. It will be in your exam. You want me to tell you what are the questions will be in your exam?
Sure.
Okay, I'll suggest 10 different biosynthetic pathways. Right? So in your exam, maybe three response. That means you have to draw a pathway. One of them could be beta oxidation. One of them could be biosynthesis of lipid. Does it make sense? One of them is the ketone body synthesis. Cholesterol biosynthesis. Correct? Prostaglandin biosynthesis. What else did you study? No. That's not it yet. Hold on. Yeah, lipid. Draw the structure of a lipid and tell me the mechanism of something. Phospholipase A2 or something. Correct? I can ask, draw the structure of di-olesyl phosphatidyl serine and tell me how phospholipase A2 reacts on this, draw the reactant and product. Does it make sense? One of these you will have for sure. One mechanism. Maybe I will ask HMG-CoA reductase, acetyl-CoA carboxylase, HMG-CoA synthase. Any of these reactions, correct? Mechanism I will ask. Draw the chemical reaction catalyzed by this enzyme and write down the detailed mechanism. Is it clear? Then another question I will have. So one mechanism, one detailed pathway. You need to know, if I am asking you pathway, you need to draw the structures of, correct, each of them. Draw the enzyme, cofactors. Each of them I like to see to get 10 points. If you don't draw the structure, you get 1/3. Okay? So draw the structures, and in the reaction mechanism, I like to see the arrow going very nicely. The direction it should go. I can ask you to draw the structure of Tylenol and tell me how it is working. Something like that. And let's go to the lipid section. Lipid is chapter 8-9. Basic properties of lipid, structures. Basic properties of lipid, fatty acids. You want to know the palmitic acid, stearic acid, oleic acid, arachidonic acid. These few structures. No, correct? I can ask, draw the structure of these. Lauric acid and myristic acid, 12 carbon and 14 carbon. They are saturated and unsaturated version of these. Does it make sense? Yes or no? Yes. Okay. Their properties, triglycerols. Then all of the head group containing lipid structure. Properties of cardiolipin. Correct? Phospholipase A2 mechanism. Structure of it. PAF, platelet activating factor, correct? Sphingolipids, they are amide containing lipids, correct? Then you go for, you want me to give this one?
No.
See, I listen to you. Waxes, properties of waxes, terpenes. What is the monomeric unit? Isoprene, correct? So, and then some of the, which one of the following is an example of a terpene? I will pick up one of them, but I want you to know limonene, citronol, menthol, correct? Lycopene, lanosterol we did, guanine we did, camphor to campene, gibberellin. I think all of them you should know because these are. You don't have to know the structure. Okay, you don't have to know the structure of these. Just know the name, where from they come, and it is a terpene. Is it too much? Okay, good. So you don't have to know the structures, but know that they are terpenes and their name and their origin and the property. Correct? Then you go for steroids. I want you to know the structure of cholesterol, testosterone, estradiol, cortisol, and maybe cholic acid. Estradiol, testosterone, cortisol, cholic acid, 4. Does it make sense? Structure. I don't expect you to know the structure of the plant, but I want you to know that stigmasterol and the family is the plant-based steroid. So I can ask which one of them is a animal-based, which one is a plant-based. Does it make sense? So that you are familiar with some of it. Then membrane properties, very important. Transition, thermal transition, melting temperature, effect of unsaturation on melting behavior. Alright? If you increase the amount of cholesterol, what will happen? If you increase the amount of unsaturation, what will happen to the melting temperature? If you increase the chain length, what will happen? Does it make sense? Yes or no?
Yeah.
Good. See? So, and then you go for phase transition we have done. Yeah, it's done. Then we have chapter 23, I guess. Fatty acid, degradation. Nothing is omitted in beta oxidation. You want to know everything, correct? You start with the unhydrolyzed lipid to get free fatty acid. Then every detail of beta oxidation of saturated fats, correct? And the reaction mechanism. And then you go for, I'm not summarizing anything, function of carnitine, draw the structure of carnitine and tell me how it helps in fatty acid degradation. Correct? So you have to draw the structure of carnitine. So insulin, I think I was confusing you other day. Correct? Insulin actually helps producing lipid biosynthesis, activator of lipid biosynthesis. So insulin, if you have glucose glycolysis to pyruvic acid and then acetyl-CoA, correct? This is insulin is positive regulator of this pathway, correct? So insulin is also, if you have any other pathway where the acetyl-CoA is reduced, if the intermediates are reduced level, then this reaction will be facilitated. Does it make sense? So if you take away the acetyl-CoA by some way, that will be facilitated by insulin. Does it make sense? If you synthesize the lipids out of acetyl-CoA, level of acetyl-CoA will go down. So insulin does activate the synthesis of fatty acids, inhibits the degradation of the fatty acids. Does it make sense? That's how it is. Okay, so know the carnitine, know the function of insulin, glucagon, and epinephrine in beta oxidation and biosynthesis. How it will regulate? Some of the regulators, citric acid, how it is going to regulate? High citric acid will regulate in which way? The lipolysis versus fatty acid biosynthesis. Does it make sense? So regulation definitely will have some question. So know this beta oxidation pathway in detail, the mechanism and the enzyme. So then we have what? Odd carbon chain fatty acid. How many acetyl-CoA is produced from even and odd? If it is unsaturated, briefly touch. I am not going into detail how they may be metabolized. Okay, brief. And then you have the ketone bodies in biosynthesis, and they are significant in diabetes. Is it clear? So that's this, and then we have chapter 24, lipid biosynthesis. So start with acetyl-CoA carboxylate, correct? Detailed reaction mechanism, malonyl-CoA, and then the detailed pathway. This is the mechanism of acetyl-CoA carboxylate. Then you have regulation of acetyl-CoA carboxylate, correct? Insulin, glucagon, epinephrine, high acetyl-CoA, high citric acid. Does it make sense? So those basic, and then you go for the biosynthesis. How from acetyl-CoA you make a 16 carbon saturated. I can ask you, draw the pathway for synthesis of palmitic acid starting with acetyl-CoA. Does it make sense? Yes or no?
Yes.
Okay, good. Then you go for with regulation. Then I said cyclooxygenase reaction mechanism, the significant structure of 3 non-steroidal anti-inflammatory drugs, aspirin, Tylenol, ibuprofen, and how they inhibit mechanism inhibition, correct?
Right.
Inhibition of cyclooxygenase, that one. And then we have the cholesterol biosynthesis starting with acetyl-CoA. How will you make cholesterol? I already told you from acetyl-CoA to detailed mevalonate, squalene, ranosterol, cholesterol. Does it make sense? So that you can do also with the limited time. And how these cholesterol lowering drugs, what is the structural moiety in the active site of this well-known cholesterol lowering drug. I will, if you want me to ask the structure of a cholesterol lowering drug, I could do that. You don't want? Okay, so will not ask, but I will ask. Correct? What active site is here? What is the active site in this libitor? What is the active site in lower setting? Correct? Any other question? I may ask you 4 free response, but you may not have a lot of time to draw. Correct? 1 free response may be just 1 line answer. That's 10 points. Okay? So something like that.
But Professor,
Okay. There will be 1 bonus question.
10 points.
No. Bonus question, normally what I give, it has no right and wrong answer. Okay? Yes.
Can you go over the active sites again?
Here is the active site.
It's lactone.
The mevalonic acid, the active one, correct? So, maybe 15 multiple choice. Bring a scantron times 4. 4 short answer type times 10. 1 bonus 1 5.
What?
1 question 5 points. So it will be 105.
will all the short answers be mechanisms in pathways?
These are all going to be. I told you what I am going to ask. Huh? If you have studied all of it, whatever I said, you get all of it. Any other question?
The little green scantron or the big blue one?
Little green, no, get the tall one. 82 or something. 882.
Green?
Yeah. Okay. Any other question anybody has? Yes.
So we have to know the structure for like the biotin and the NADH and all.
Those you need to know from BIOCHEM 1.
I just want to make sure you want to actually see.
Yeah. I can ask you draw the structure of biotin and tell me, or draw the structure of NADH. Tell me how it helps it catalyzing the hydride transfer. It's in the book. Yes. If I ask NADH structure, draw the detail, but if you are using in the reaction mechanism, just use the active site. Any other question? Alright, enjoy the exam because I will be enjoying in Washington DC.